Assalamu alaikum. In this video, we are going to solve a problem about the first lesson, energy. Let's remember the main ideas mentioned in the lesson. Pause the video to take notes if you need to. Problem 1. A string of negligible mass connects two solids of which are considered as particles of masses m1 and m2. The string passes over a pulley of negligible mass which is fixed at the top of an inclined plane, which makes an angle alpha with the horizontal OA. The string is inextensible and doesn't slide over the pulley. The friction along the incline has a constant magnitude F. At t equals to 0, the particle S2 is at height h2 equals to 30 meters above the ground level OA, and the system S, which is S1, S2 string pulley, is released from rest. Take the horizontal plane containing OA as a reference level for gravitational potential energy. The string is inextensible, then the sum of the works done by all the tension forces along any displacement is 0. Part 1. Determine at instant t equals to 0 the expression of the mechanical energy of the system in terms of m1, m2, g, h1, and h2. First, what is the expression of the mechanical energy of a system? It is the sum of the kinetic energy plus potential energy. But we know that the pulley is of negligible mass. Thus, its gravitational potential energy and kinetic energy are zeros. Then, mechanical energy initial at t equals to 0 can be written as the kinetic energy of the particles S1, S2, and the pulley, plus the potential energy of S1, S2, and the pulley. But initially, S1 and S2 were at rest. The mass of the pulley is 0, so its kinetic and potential energies are zeros. Then mechanical energy is written as m1 gh1, which is the height at t equals to 0 h1, and m2 gh2, which is height h2 of s2 at t equals to 0. Determine at instant t the expression of the mechanical energy of the system in terms of m1, m2, h1, h2, g, alpha, v, and x. So at any time, the mechanical energy can be written as the kinetic energy of the particles S1, S2, pulley, potential energy of the particles S1, S2, and pulley. The same idea, the kinetic energy and the potential energy of the pulley are zeros. So what are the kinetic energies and the potential energies of S1 and S2? So they can be written as half m1 v1 squared plus half m2 v2 squared as kinetic energies. But according to this potential energy, which is m1 gh, let's see how can I find the height. At a given time, S1 will be at a given height above ground, and it will move a distance x along the incline, but forming this right angle triangle. This is x, and this is angle alpha. So what should be this small height? It is the opposite of alpha in this triangle, and it can be written as x sine alpha. Then the total height of this point at a given time, t, is given as this small height plus the initial height, which is h1. And we find m1 gh1 plus x sine alpha as the potential energy of this particle at time t. On the other hand, S2 has a height h2 minus x because initially it was at a height h2, but moving a distance x, this height will decrease, thus having a height h above ground less than h2, and it can be computed as h2 minus x. Expanding this expression, we can find that the mechanical energy is half mv1 squared half m2 v2 squared plus m1 gh1 plus m1 g sine alpha x plus m2 gh2 minus m2 gx. But the string is inextensible, so at any time v1 of S1 will be equal to v2 of S2 equals to v. The same for the distance covered here, which is x, will be equal to x covered by S2 also. Now, taking v common and x common and rearranging this equation, we can find that half v squared into m1 plus m2 plus m1 sine alpha minus m2 into gx plus m2 gh2 plus m1 gh1 is the expression of the mechanical energy at any time. Using non-conservation of mechanical energy of the system, show that V squared equals to this expression. Why they said non-conservation of mechanical energy? Because in the given of the question, it was mentioned that the friction along the incline has a constant magnitude F. So since friction exists, it is a non-conservative force, so we can say that the mechanical energy of the system is not conserved. In this case, we can say that delta mechanical energy equals to the work done by friction, which is minus Fx. We should find the mechanical energy at two different instances to calculate delta m(E). So we have mechanical energy initial at t equals to 0. We have found it to be m1 ch1 plus m2 ch2. In the second part, we have found that mechanical energy at any time, V squared over 2, m1 plus m2 plus etc. If we subtract both factors, mechanical energy final, which is at a given instant t, minus mechanical energy initial, we can find that we have common factors m1 gh1 plus m2 gh2. If we subtract them, we can cancel them. Then delta m, which is mechanical energy at a given time t minus mechanical energy 0, equals to m1 plus m2 into half v squared plus m1 sine alpha minus m2 gx. This is found in one side, and the other side it is equal to minus fx, which is the work done by friction. We get the answer v squared equals 2 times m2 minus m1 sine alpha into g minus f, x is common, over m1 plus m2. Deduce the expression of the acceleration a of s as a function of f. Deducing it means that we should go back to the expression of the velocity v squared. S is in rectilinear motion. Thus, v is the derivative of x and a is the derivative of v. To find the expression of the acceleration, we should derive the expression of v squared. Deriving v squared is 2v prime, where 2 into m2 minus m1 sine alpha g minus f over m1 plus m2 is constant. So it is the coefficient of x and derivative of x is just v. Now by comparison, we can say that v prime, which is the acceleration, is equal to m2 minus m1 sine alpha g minus f over m1 plus m2. Replacing the masses by their values, where this and can be computed, we get also a equals 2 minus 10 1 minus f 5 by replacing the above document shows the variation of the masses alpha g. Referring to the graph, determine the value of the friction f along the inclined plane. But we have found in the previous part an expression of v squared as a function of x, which also represents an equation of a straight line passing through origin with a slope b equals to all this factor. According to the graph, also we have an equation of a straight line passing through origin with a slope. We can find it, where b can be found by replacing masses alpha g by their values, and the answer is 2 minus 10 f. From the graph, since they said referring to the graph, it represents a straight line passing through origin, and its slope can be found by delta v squared by delta x. Taking these values, delta v 10 minus 0, where at this position x is 20, and 20 minus 0, 10 over 20, the answer is half. Comparing these two answers, half equals to 2 minus 10 friction f. Friction will be 0.15 in newtons. Deduce the value of the acceleration x. Simply, from part 3, a equals to 1 minus 5 f. F is 0.15. The answer is 0.25 meters per second squared. Determine the time t1 taken by S2 to reach the ground level. Look back to the graph. At 30 meters, v squared will be equal to 15 meters squared per second squared. Because 2 divisions equals to 10, then a division is 5. 10 plus 5, it's 15 meters squared per second squared. When v squared equals to 15, then V1 at t equals to 1 is radical 15 and it's 3.873 meters per second. V equals to antiderivative or the integral of A dt. Now between 0 and t1 the expression is AT plus V0. A is constant, then the antiderivative of constant is AT plus V at t equals to 0 at t1. This expression will be V1 over A. V1 is 3.873, it's found in this part. A, it's found in the previous part. Divide them, T1 will be 15.132 seconds. This is the end of problem number 1.